Part B.3, Horner's rule. This is the last video of this part, Part B, Power of Algorithms. In this video, we will learn a very smart algorithm, Horner's rule. Actually, from the previous video, we got part of it. Remember, when we work on a quadratic formula, we did something that is pretty much give us some idea of that Horner's rule. All right, so let us do the whole thing another time. Okay. Let's recall in our quadratic formula, when we work on it, we did a very important step, factorization step. So look at this. The factorization step give us this transform. Remember? The transform step gives us a different structure of the polynomial. So this new structure reveals some insight, some important insight that can give us a better solution. So that's the reason we do this. Okay. All right. So now we want to generalize this simple, effective idea to the general case, the general polynomial case. Yeah. All right. Here you can see the key of success is factorization. Yeah. From this work, we summarize why we get this nice result. The key of success is factorization. Okay. All right, since this is the big reason for the success, so we want to use this great thing as much as we can. Right? Yeah. It's something very important for this particular problem. So we want to use this factorization idea as much as we can. Okay? Yeah. So that's the natural logical reasoning. Right? Yeah. Strategy for generalization. So strategy another time. Yeah. For generalization. Yeah. Do factorization as much as we can. That simple strategy, as much as we can. Here. Okay. So I emphasize this part, as much as we can. It's pretty vague here, but you get some idea. So what do we mean, as much as we can? Yeah. So this way, this method, so usually we call it greedy idea. So to be greedy, so we try to get something as much as we can, right? To be greedy, So this is a special name for this method. So later we will learn a special method called greedy algorithms. Greedy algorithms. Yeah. If we have a chance, at the end of the semester, we may not have that much time, but this greedy algorithm, in this course, we will use this idea several times. So this is the first time we use this idea. Okay. All right. Let's do the work. So we have the strategy. Now, let me show you how to do the factorization as much as we can. Now, here I use n equals 3 case, just another special case. Yeah. But when we work on this one, you can get idea for the general case. Yeah. All right, so the factorization should cover as many terms as possible. This is our interpretation of as much as we can. How to implement the idea as much as we can. So we try to put a little more details there. Factorization should cover as many terms as possible. So that's the implementation details. So now we follow this guideline, try to make it work. All right. First, when we start, we do factorization. We cover as many terms as we can. How many terms have common factor x? The last three terms. So we do factorization to cover last three terms. Right? Yeah. So we get one step factorization. The first step. Second, next, inside the parenthesis, we have another smaller polynomial. Can we apply this factorization technique another time using the same idea, right? Yeah, we can do it. Yeah. So now inside the parenthesis, we do the factorization that covers as many terms as possible. So we get another round factorization like this. Okay? Keep doing things. So if we have a long polynomial, can we do this again and again from beginning to end to get as many factorizations as possible, right? Yeah. The answer is yes. We can easily envision that, right? So, use our, mental visualization, okay? So finally, we can get this. Push to the general case. Do factorization in this way. See? In this way. Okay? Yeah? Right? Step by step, level by level, from beginning to end. Okay? Finally, we get this structure. Okay? That is the Horner's rule. That's the so-called Horner's rule. Very simple, very smart. The result is really good. Yeah. So we will see the excellent result soon. Yeah. All right. Next, we want to count the number of multiplications. Okay? And when we count the number of multiplications, here I use the same counting method I did in a previous video when we count the number of additions. Counting by reference. Here, remember, we need to create one-to-one correspondence between object 1 and object 2. Right? So then, we just count the number of object 2 to give us the number of object 1. Okay? So that's the simple way we're doing here. Object 1, number of multiplications. So x times parenthesis. Okay? Result inside that parenthesis. Okay? The first multiplication. Then second multiplication. And so on. And until we get to the last multiplication. But it is very hard to keep track of all these multiplications. There is no reference associated to this multiplication directly. So for, then we try to create another convenient reference, one-to-one correspondence. The first multiplication we want to associate with the subscript of A1. How about that? Okay, because it is very close to A1 coefficient. So we do that association. Okay. Second multiplication we associate with A2, subscript 2, and so on. Okay. In this way, the last multiplication associate with the last coefficient, an, the subscript n. Okay. This is a 1-to-1 correspondence. And counting number of subscripts, so easy, very simple, right? From 1, 2, 3, all the way through n. Okay, so that number is n. Then we can say the number of multiplications used in this way in Horner's rule, n. So we get a conclusion. Number of multiplications, n. Okay. So now you can see we get a new solution. Horner's rule solution, new solution. Okay, yeah. This new solution gives us this kind of multiplication reduction. How good is the reduction? So let's compare. Old method, actually we have a name for it. Yeah, brute force method. Brute force method. Yeah. So later we will have one whole section to cover that brute force method. Here we use it. The brute force method just gives us this many multiplications to evaluate a polynomial, okay, of degree n. Then Horner's rule reduces that number to just n. Here the question is, how much is the reduction? Is that reduction big? Right? How big it is? Yeah. So our next question is, we want to look at how big is the reduction. Remember the title of this video, or the title of this part B, power of algorithms. And I select this example from chapter 6 because I want to show you the power of the algorithms. So my next slide, I will show you how big is the reduction. From that big difference, you will see the power of the algorithms. All right, so let's look at that part. All right, impact of multiplication reduction. Okay, yeah, the impact. We can imagine the impact. We improve the performance significantly. But how big it is, at this point, we cannot imagine. Because when you look at these two numbers, how can you get a visualization of the difference of those two expressions? So it's very hard. Just two expressions, hard to visualize. So here I like to use some special examples to help us visualize that difference. Yeah. All right. To do that visualization, yeah, let's just try some simple examples. Yeah. The first one, when n equals 1,000. The first example, 1,000. Okay? Degree 1,000 polynomial. It's possible. Yeah. So let's look at how to evaluate how many multiplications. We only look at the multiplications. Yeah. Based on this formula, we can see using Horner's rule, we need 1,000 multiplications. Use the brute force method, right? Brute force method, all right? Yeah. 500,000. So you just plug in number. Here I use some approximate number, not exact. Yeah. Many times we don't need to use exact number. Yeah. So in our computer science, in most of the situations, approximate numbers good enough. Okay? So here we use it approximate. It's a very good approximation. 500,000. The ratio, very simple. You can see 500 to 1 ratio. Is that big? 500 to 1. Okay? Yeah. So the brute force method, you need to use 500 unit of time. But if you use Horner's rule, you only use 1 unit of time. Is that difference big, right? 500th of the time. Okay, yeah, so that's the first example. The second example, now we want to consider a much bigger polynomial with degree 1 million degree. N equals 1 million. Okay, now the Horner's rule still, yeah, same number, 1 million multiplications. Okay, then let's go back to the brute force algorithm. Brute force, this time you plug in that formula, approximate answer. Look at this expression. Look at this expression. Okay, yeah. 500 billion, right? 500 billion. Million, billion. Okay, 500 billion. Okay, yeah. That many multiplications. Imagine that number. Yeah. The ratio is 500,000 to 1 ratio. 500,000 to 1 ratio. If the brute force method uses 500,000 units of time, the Horner's rule, you just use 1 unit of time. That big difference. Okay? Yeah. Here, let me just do another form change to give you better visualization on this big difference. Okay? For convenience, here I select time unit second. 1 time unit as 1 second here for convenience. Okay? So then, if we use the Horner's rule, we just need to use 1 second, 1 unit of time, right? 1 second. Tick, so fast, you get an answer. Okay? Yeah, Horner's rule. Now, we do the same thing using the brute force method. Okay? Brute force method, yeah, on the same polynomial. This time, based on our calculation, we need 500,000 seconds. How long is it? We try to visualize. How long is 500,000 seconds? Okay, so I just do the conversion. Okay, so you can do it easily by yourself. Approximately 5.8 days. Slightly less than 6 days. 5.8 days. Is that long? How long? Yeah. So you hit the button, then you need to wait 5.8 days to get answer. Okay? You need to wait for 5.8 days to get answer if you use the brute force method. If you change it to Horner's rule, you hit the button, you hit the key, right? Return key, you hit the key, then after 1 second, you'll see the answer. Compare the difference. Okay? Yeah. So that's the huge difference. Okay? So our visualization is reflected by these two numbers, 5.8 days versus 1 second. So using this simple example, I want to let you feel the power of algorithms, how powerful it is. Choosing a smart algorithm like Horner's rule, you get 1 second response time. If you do not know Horner's rule, you just do it using the brute force method. You need to wait 5.8 days to get the answer. Think about it. That's the reason we want to learn this algorithms class. We will do that smart way, not the dumb way. Okay. All right, so let me finish this video and the whole part B for this class. Yeah.